Today, we are going to talk about how to perform DFT simulation to calculate the phase transition pressure of silicon. So we are going to compute the pressure between the silicon diamond structure and the beta tin structure. We are going to use the Ebonite DFT program to do the simulation, and the PAW datasets are coming from the GRBB website. So first of all, we try to find the equilibrium lattice parameter for a silicon diamond structure. We set the OPT cell equal to 2 here to do the full optimization of the structure, which means that we also optimize the lattice parameters as well. After relaxing the structure, we obtain the optimized A cell and the R prime from the silicon.out file, and then we know that how can we change the lattice parameter to scan it and to get the equation of the state. So then we use this NTD set function in Ebonite. We set it to be 6, which means that we are going to perform 6 separate single point DFT simulation within Ebonite. And for each of them, we are going to have different lattice parameters. So that's why the starting value for the ACL is 7.1 and the bar, and we increase ACL by 0.1 bar at each time each step. So by doing that, we can scan the lattice parameters of the silicon diamond structure, and this is the total energy coming from that. You see that we have 6 different energies from this scanning. Because we are going to do the energy versus volume plot, so we also need the volume from the calculation. If you grab the UC volume from the silicon.out output file, you'll get the volume from it. So now we can fit this energy versus volume data to the Monahan equation to get some key parameters for the equation of the state. We are going to get the bulk modulus B non, and also the dB non dP, which is the pressure, the derivative of the bulk modulus with respect to the pressure, and also the V non, which is the equilibrium volume, and also this constant term, which is actually the equilibrium energy. So now we pass this energy and volume to this equation. Here I give you the MATLAB script for doing the fitting. I put the energies here and put the volumes here. By the way, the energy and the volumes are coming from this DFT simulation. And the initial parameters are here. And I do the least squared fitting in MATLAB. And after that, if you want to know the bulk modulus in the SI unit, you can convert it from the atomic unit to SI. Because by default, all the units from Ebonite are in atomic units. So we have to convert that into the SI. And this X is very important, which is the return value from the least squared fitting. We are going to use this X to define the equation of motion for the silicon diamond structure in the next sections. So here is the definition of the Monahan equation of a state. You see that this formula is very similar to this formula here. After running this MATLAB code, you will get the return values of X. So the first one is the bulk modulus of our silicon diamond structure. The second one of X is a dB/dP. The third one is the equilibrium volume. The last one is the constant, which is the equilibrium energy. If you want to double check that your calculation is correct, you can compare your calculation with the experimental values for the bulk modulus of silicon diamond structure. So in my calculation, I got 103 gigapascal. In step 2, we study the beta-tin structure of silicon. Again, we try to relax the geometry of the beta-tin structure first. We set the optimal cell to 2 to perform a full relaxation of the beta-tin structure, including relaxing the lattice parameters. And the initial geometry for the beta-tin structure is given here. So also the positions of the 2 atoms inside the cell is given here as well. After relaxing the beta-tin structure, we need to compress or stretch the volume of the beta-tin structure to get the equation of the state for this material. So what we are going to do is that we are going to perform constant volume relaxation of the beta-tin structure by setting your OPT cell parameter to 3. And in the meanwhile, again, we change the lattice parameter by stretching or compressing the A cell parameter in the calculation. So here my A cell starting from 6.65 Bohr, and the increment is 0.1 Bohr. And we are going to do this for 6 different points of the A cell. And for each given A cell, we relax the geometry, but holding the volume to be constant. In the end, we get the volume for each of this job, which is here, and we also get the energy for each of this job. After plugging these volumes and the energies of the beta-tin structure into the previous MATLAB program, and we can get the equation of states for this beta-tin structure as well. And this X parameters is the results from that fitting, and we are going to use it. After getting the equation of states for the diamond structure and the beta-tin structure, now we are in a position to calculate the transition pressure between these 2 structures using the common tangent method. And let me go to the end of this PDF to quickly show you what does this mean. So this is the final plot we want to have. So this yellow curve is the equation of motion for the beta-tin structure. And this red curve is the equation of states for the cubic diamond structure. And you can see that because we know that the cubic diamond is the lowest phase of silicon. So that's why the energy of these red circles is lower than this beta-tin structure. And this blue line is a common tangent, which is tangent for both curves. So I'm going to show you how to use MATLAB to make these plots and find the common tangent. So this is the MATLAB script we are going to use. So first of all, we copy and paste the previous equation of state parameters we obtained for silicon diamond structure here, this one. We copy and paste it to be here. And we also copy and paste the parameters we obtained for the beta-tin here to here. So we are using fmin search function, try to minimize this objective function, try to find the common tangent between the 2 parabolas. Okay, so now let's take a look at what does this objective function do in practice. So the object function is defined here. And basically speaking that you just pick up 2 points on the volume axis. For example, 1 point here and 1 point here. And then you calculate the derivative at these 2 points on these 2 parabolas. And in the meanwhile, you also calculate the slope between these 2 points by doing the finite difference method like this. So the idea is that if we have the common tangent between these 2 curves, then that means the tangent here, the tangent here, and the tangent through the finite difference between these 2 points, they should be the same. So that's why the object function is defined as dy minus d2 squared plus dy minus d3 squared. So the f-mean search is just try to minimize this object function, try to find the common tangent between these 2 curves. In other words, this f-mean search function try to find the 2 points on these 2 curves that can give you the common tangent. So at the minimum, then we got our solution. So then we do the plots. So you can see from here, so we first plot the common tangent, and then we plot the equation of states for the cubic diamond structure, and we also plot the equation of states for the beta-tin structure. So in the end, we got this plot. So the transition pressure is just the slope of this line. You see it's negative, so it's minus 9.61 gigapascal. And this transition pressure compares very well with the reference, which is here as well. Okay, so that's all the discussion about doing DFT simulation to find the transition pressure between 2 phases, cubic diamond structure and beta-tin of the silicon. And you can use a similar method to calculate the transition pressure of other structures as well. I hope you find this tutorial useful for your research, and see you next time. Bye-bye.